Hello and welcome to another power electronics class. In the previous class, we finished the buck boost and buck boost converter chapter, and we also discussed the continuous conduction mode and the discontinuous conduction mode, and the critical point, the critical current, the critical inductance for the continuous conduction mode and the discontinuous conduction mode. We also learned about the uncertain point as well, uncertainty that we have and the worst case scenario. And the worst case scenario, as you may remember, is when the load or the source changes. Now, today we're going to discuss the design of feedback controllers in power electronics and the importance of the controllers in a converter. So in this chapter, we would discuss the need for feedback controllers in power electronics, the basic principles, and we will be focused on the regulated switch mode power supplies. First, we will design the feedback controllers in power electronics. I will give you some examples. The need for feedback controls in power electronics, basic principles and specific focus on regulated switch mode power supplies. And then we will go through the regulated power supply and different methods that we can implement it, such as the voltage mode control and peak power control, peak current control. Some applications of feedback controllers are, for example, in electric generation in wind turbines, photovoltaic systems, electric drives in transportation, and regulated switch mode power supplies. Why do we even need a feedback control, for example, for a wind turbine system? So let me give you an example. Imagine we have a car battery, and the car battery is not charging. It's just sitting there. We're using it as our power source. And initially, it's fully charged at 12 volts, for example. And I'm at a campground or an RV park. And I have this DC to DC converter. And I have a boost converter or a buck boost, whatever. And I'm charging my laptop, which is let's say I have a computer or laptop. I'm working, offline. And I'm charging the computer, the system, and I'm actually supplying the system with this battery. And this system, let's say, works on 19 volts. Okay, so I'm charging a monitor, and assume both of them are working on DC. Okay. Now, initially, everything works perfectly. Do you remember what the equation was for a boost converter? V out or Vn is equal to what? T. Is it correct? Okay. So now if V out is 19 and Vn is 12, what would my duty ratio or duty cycle be? For the purpose of making it easier, let's make this 24 volts. So 24 over 12. So it's going to be 24 minus 24D is equal to 12. Am I correct? So 24D would be equal to 12. Therefore, D would be equal to what? Half. Yes? Okay, or 50%. So you would set this has imagine this has a knob that you can turn, and you can put it on 50% D ratio and leave it there, and you're going to have 24 volts at the output. But the problem is, since this battery is sitting there, it's not being charged, it's an off-grid system, the voltage is reducing, it's discharging. Now, when the voltage drops to 10 volts, and we haven't changed the D ratio at all, what happens is now we want to find V out. V in is 10, and it's 1 over 1 minus half. So if I calculate, the new V out now would be 20 volts. Okay. Some computers work up to like 5%, 10%, up and down. But 20 volts, what happens is that the computer will shut off. Okay. It's not going to work on 20 volts, for example. So if I have a normal boost converter, which is manually controlled, the system would stop working after, let's say, like 20, 30 minutes when the voltage, depending on how big our battery is. And we have the same scenario for wind turbine as well. Imagine we have a wind turbine that it's initially, let's say we have a wind turbine or a PV panel that it's initially turning at, let's say, 10 round per minute, something like that. And when it's running at 10 round per minute, it's generating 40 volts, for example. But then the wind drops to 5 round per minute, and the voltage drops to 20 volts. And I have connected this time to a buck converter, and imagine it's a DC generator. We also have DC wind turbines as well. And that has a duty ratio of 50% again. The output voltage is 20 volts now. And when the wind drops, what happens? The voltage drops to 10 volts. Okay. So whenever we have a source or a load, and it's the same thing for a PV panel as well. Again, if we have a PV array of systems during morning, it's producing, let's say, 45 volts. At noon, it's producing 80 volts. And in the afternoon or evening, it's creating like 30 volts, okay? And we want to have a solid 12 volt in the output, for example. We cannot build this with a normal buck converter. We must have a system that we can actively control the duty ratio. And what was the duty ratio or duty cycle? It was the switching speed. Do you remember? It was the frequency, the switching frequency, okay? Because D was T on over TS, if you remember. So by changing the frequency, the on time, you can change that. Now, in order to be able to control that, we need to be able to measure the output voltage, because we want to, let's say we want to fix our output voltage at 24 volts. Therefore, what we need is we need a voltmeter to first measure this voltage. Imagine that we have a voltmeter, and then give it through a control system. I'm going to call it K, and feed it back to the switching. Right? So what happens here is whenever the voltage drops, let's say, to 20 volts, the control system would increase the duty ratio. Let's say from 50% goes to 55%, something like that. So we need to have a real-time measurement from the output and have a feedback system to feed that back into our switch and control the switch. Is it clear up to this point? Okay. Now for the feedback system, you're already familiar with the control systems, and you had control systems. Did you pass control system, or both of you? Okay. So this class, that's the control system for finding the poles and the zeros and etc. That's a topic for control systems. What we do today, and for next class probably, is just touch base on, do a quick, review of the control systems in a power electronics. We're not going to get deep into the control system because, again, that's the topic of another class and we don't want to overlap. But for a control system, we have some objectives to be able to design the feedback of these controllers. These objectives that we have is we need to have zero steady state error. We need to have a fast response. We need to have low overshoot, and we need to have low noise susceptibility. And you can see here, by increasing gain, we're gonna probably have overshoot. As you remember, I don't know if you had that in control system, but we have overshooting, undershooting, and if the gain is too low, it's not gonna reach the final voltage. If it's too high, it's gonna overshoot and it's gonna resonate, which is not good. So we're gonna have the right amount of feedback control system for the feedback. Now, the steps in designing the feedback controller, we first need to linearize the system for small changes around the DC steady state operating point. We need to design the feedback controller using linear control theory, and we need to confirm and evaluate the system response by simulations for large distributions or disturbance. Now, this is a graph of a regulated DC power supply, and we can use a simulating tool. As I mentioned, it's better for you to just get familiar with them. We're using PSPice, MATLAB, any other simulation tools. And in the graph, you can see we have a DC to DC converter, which could be a buck boost, anything. And the important part is we get a sample from the output, for example, the voltage, and we have a reference voltage that we give it to the system. Imagine that we have a reference voltage of 20 volts. The output voltage is, say, 22 volts. And we feed that to the controller, and the controller controls our duty ratio, or D, or in other words, T on to TS, and frequency. And we have the input voltage that could be connected to a battery, a DC power supply. We don't have any control on the input voltage. The only thing that we have control over is the duty ratio. And we can do that using an op-amp easily, or we can use a programmable system like Arduino, Raspberry Pi. So this could be a fixed system like a op-amp. The controller could use an op-amp and other electronics, or you can use the Arduino system, and I'll explain how we do that to be able to program it. So for applying linear control theory, again, these are the graphs that shows that. We have the input, we have the controller, we have the pulse width modulation, or PWM, and we have the power stage and load. And finally, we get a feedback and feed it back to the system. And this is the linear control graph. And for a small signal representation, again, we have the controller, the PWM, and we have the power stage plus an output filter. And we feed it back through a feedback. You can see KFB as the feedback gain that we have. Now V out here would be V out plus V hat of D and so on, and D is going to be D hat D, and VC is going to be VC plus V hat C. Now the loop transfer function here, the GL would be equal to GC, which is the controller, plus GPWM, which is our pulse width modulation, plus the power stage, or if we want to do it in dB, it's going to be plus. If we just want to multiply them, it's a cascading, so it's going to be GL, it's going to be GC, GPWM, GPS, and finally, this is, by the way, GPS, and this is the feedback loop gain. Again, in decibels, when we want to do that, you can logarithm, you can just add them together. Both ways are correct. Now these two graphs, the upper graph shows the loop gain magnitude at the phase margin FC. As you can see, at FC it's 0. And it also shows it at gain margin, which is around negative like 40. By the way, this is in dB. And in the lower graph, we can see the loop gain phase. Again, we have the phase margin at around negative 90. Again, not negative 90, but around that. And then at negative 180 degrees, you can see the gain margin as well. And for the phase margin phase would be equal to phi L FC minus negative 180 degree. So it's going to be phi of L at the frequency, the critical frequency that we have, FC, plus 180 degrees. This shows an example. Again, I'm not going to go into the proof and depth of it, but this shows an example of the logarithm of the angle of t and the frequency response of t. And you can see that around 20 log of k, we have a sudden drop. And this is going to be our cutoff frequency, which is around 0.7 of the maximum that we have. And at this point, we have mean frequency, and you can see that the angle starts from 0, goes down to negative 45, and finally to negative 90 degrees. Now Ts in the system is going to be K over 1 plus L over omega 0, and 20 if we want to write it in the logarithm equation and find the magnitude of T. It's going to be 20 log of T j omega is going to be 20 log of K over square root of 1 plus omega over omega 0 square. So just keep in mind these two equations. So the plots of the transfer function with poles and 0, if we want to show it with poles and zeros, again, we have the same thing that we had over here. And a pole in a transfer function, Ts, is going to be 1 over 1 plus S over omega p. Now, to find a 0 in a transfer function, Ts is going to be equal to 1 over S plus omega z, which is the 0. And a right-hand plan 0 in a transfer function, Ts is going to be this time 1 minus S over omega z. You can see the difference between them. One of them is 45 degrees, the other one is negative 45 degrees. And one is becoming positive, the other one is negative. But the magnitude, both of them are going to be equal to positive 1. You can see the 0 in the transfer function here. Now, 2 poles in a transfer function, if we have multiple points, we're going to have a nonlinear situation here. And by increasing that, you can see that we are increasing the overshoot by increasing eta. And the transfer function Ts is going to be 1 over 1 plus alpha s plus s over omega 0 square. And for different alphas, you're going to have different situations of overshooting. And if you have a higher alpha, you're going to have a more square signal in the phase shift and a sudden phase shift in the system. But the thing is, if you're going to have a smaller, smaller alpha, you're going to have a more square shaped in a sudden drop in the phase. But in other words, you're going to have a overshooting situation as well, and that's not good. So you're going to have a trade-off. Best scenario would be the alpha to be in the middle, not close to the maximum or the minimum, so something in the middle, depending again on what type of circuit do you have, depending on number of poles, number of zeros, a lot of factors. This is just for you to see a visualization of what happens in a 2-pole system. It becomes complicated, nonlinear. So using computer simulation to obtain the transfer function plots, the Bode plots, we have a buck converter in this example, which has the following parameters and is operating in the continuous conduction mode. L is 100 microhenry, C is 697 microfarad, R is 0.1 ohms, Fs is 100 kilohertz, Vn is 30 volts, and Pout is 36 watts. The duty ratio is adjusted to regulate the output voltage at 12 volts. So the input voltage is 30, output voltage is 12. We want to obtain both the gain and the phase of the power stage, GPS, for the frequencies ranging from 1 hertz to 1 kilohertz. Again, we are changing these to see what the GPS would be. And you can see the changes in both the GPS and its the phase and its gain as well. Doing these manually is sometimes going to be very difficult, so it's better always to use a simulation tool. So you can see at 1 hertz to 300 hertz, we are at 0 dB, meaning it's not even functioning well. And then we have a sudden increase at 300 hertz, around 1 kilohertz, and it flats out around 10 kilohertz. So around 100 kilohertz, you're going to have around negative 90 dB. Now, linearization of various transfer function blocks. We have linearizing the PWM control IC. And you can see here the PWM IC. And the equations for PWM IC, the DT, VCT over V hat R, which is the average one. And again, VCT, we can find it using the equation VC plus V hat CT. And PWM is going to be D hat TS, DS over V hat VCS. Again, these equations are just for you to know the systems. And here we see the T on or the DTS and TS. And at the same time, we see the average, the voltages that we have VR. The actually reference voltage, sorry, why did I say the average voltage? So you can see the reference voltages as well, which is the feedback from the system. So average representation under dynamic conditions, we again have the model that we discussed in the previous class. Again, here VCP, which is the input voltage, is going to be equal to dVP, which is the output voltage that we have. I'm sorry, VCP is the output voltage, and VDP is our input voltage here. Can you tell me what type of inverter this is? It's a buck converter. The easier way to find it is in a buck converter, the inductor is after the switch, right? Anyway, but the thing is, the only difference that we have from this than the normal buck converter that we saw is the control system that we have here. And the control system is controlling our switch, and therefore it's controlling our duty ratio. And we have the reference voltage coming in, and for the representation, again, we add this control system to it, and VCT is going to be 1 over the VR, which is the reference voltage that we get, and we feed back that from the output to the input. And IVP, again, exactly like a buck converter, is going to be DICP. And by adding the control system, average VCP is going to be equal to DTVVP, and IVP is going to be DTICP. Now, to continue the linearization of power stage of a DC-DC converter in a continuous conduction mode, dt is going to be d plus d hat t, vp is going to be vp plus v hat p, and when we simplify them, we get to these two equations. I hat vp is going to be d I hat cp plus icp d hat, and so on for vc hat p as well. So these two equations we got from the previous. We can model now using a different model for our buck converter. So we learned the model in the previous class, but we have a system with the control system with the feedback control loop. This would be a general model that we're going to use. So we're going to have the d hat VP added here as a voltage source. And by the way, this is a dependent voltage source, and we have a dependent current source added to the input. So a dependent current source in the input and a dependent voltage source connected to the output. Now, why do we use a dependent and not an independent? Obviously, because this changes depending on the duty ratio that we have, and also the output voltage and the input current, which are continuously changing. Now, these are some examples of linearizing single switch converters. The upper one is a buck converter that we already have, and we can see that we added the dependent current source and dependent voltage source in the input and the output. For a boost converter, we would add the dependent voltage source in the input, and the dependent current source would go to the output. So it's the opposite of a buck converter. And for a buck boost converter, we add the dependent current source in parallel with the switch, and the dependent voltage source in series with the switch and the inductor. So remember the locations of each source in these three systems, because you may have them in your next exam, in your upcoming exam. Now for the small signal transfer function for buck boost and buck boost converters. For a buck converter, the equation is this. Boost converter is the second one. And buck boost, again, you can read faster than I, so I'm not going to even try to read the equations. And a buck boost converter is going to look like that. And LE, which is L over 1 minus square 2D square, is the boost and buck boost, and the inductor for that, inductance for that. So the questions that you're going to have from this section, again, because control system is a different course, are going to be mainly just theoretical questions. And I'm going to give you an example of what type of question you're going to see in your upcoming exam. It's going to look like this. So in the linearized model of a switching power pool, the following is true. A, products of the perturbations are ignored. It is assumed that this power pole is operating with average voltages and currents that are 0. And C, it's going to be none of the above. I'm going to give you a few minutes to think on this. These are the equations that we have. So the correct answer is going to be A. We ignore the small amounts. And we don't assume that the average voltage and current are 0. So now for a regulated DC power supply, we have different type of control systems. We have the voltage mode control and we have the current mode control. And we're going to start with the voltage mode control. The voltage mode control topography looks like this. We have a DC to DC converter topology. We have the voltage measured in the output given to the input to the controller, and also the reference voltage also added to that to make a decision in the controller and feed it back to the system. The linear control topology, the graph looks like this. Again, we have the controller, we have the PWM, we have a power stage and load, and we have the feedback to the system. And adding that to the input, we have an error, which we call V error, and the V error changes the controller, that which changes the duty ratio and the output voltage. And for the small signal representation, again, we have the controller, pulse width modulation, and power stage plus the output filter. So again, we have the loop transfer function, exactly like what we had before. We have the frequency at the phase margin and the phase at the gain margin. and also the loop gain at the gain margin. And again, the phase margin, the phase margin is going to be equal to phi LC plus 180 degrees. Now, the transfer function, from this transfer function, we're going to solve an example. So I can show you the different graphs that we're going to have and using a simulation tool. So we want to design the feedback controller for the buck converter described in example 4.2, the previous one. The PWM IC is as described. Here the KFB, the feedback gain is going to be 0.2. Steady state error is required to be 0, and the phase margin of the loop transfer function should be 60 degrees. And from example 2, we had L is 100 microhenries, C is 697 microfarads, R is 0.1 ohms, Fs is 100K, Vin is 30 volts, P out is 36 watts, and V out is 12 volts. And we want to find the power stage between 1 hertz and 100 kilohertz. And again, you can see the output gain and the phase. And you also see the crossover frequency, FC, of the loop gain is as high as possible to result in a fast response of the closed loop system. The phase angle of the loop transfer function has the specified phase margin, typically 60 degrees at the crossover frequency, so that the response in the closed loop system settles quickly without oscillations. And the phase angle of the loop transfer function should not drop below negative 180 degrees at frequencies below the crossover frequency. You can see because of the phase frequency, we have a little bit of an overshoot in the system as well. But the good thing is we have a pretty sharp response, quick response. If we didn't have a very high frequency, it's going to somehow look like this, and this would have looked smoother. If we had a higher frequency response, it's going to look like this, and you're going to have an overshoot in the system. So now to solve these problems, we're going to use the K-factor method. GCS is going to be KC over S, which is going to be equal to 1, and it's the poles and the zeros, which is going to be 1 plus S over omega Z, which are the zeros, square, over 1 plus S over omega P, which are the poles, square. We introduce a pole at the origin, which introduces a negative 90 degree phase shift in the loop transfer function. The phase of the transfer function peaks at geometric mean of square root of Fz over Fp, very important. And we boost the phase at Fc by placing 2 coincident zeros at Fc to unify the effects of the 2 poles in the power stage transfer function. The coincident poles are placed at Fp to roll off the gain rapidly before the switching frequency. Now, to solve the problem, we would go through 4 steps. The first step is to choose the crossover frequency. We choose Fc to be slightly beyond LC response frequency, which is 1 over 2 pi square root of LC. Again, this is very important. This is the frequency response of an LC, which in this situation was 600 hertz. Therefore, we will choose Fc to be slightly above that 600 hertz, which is 1 kilohertz. This ensures that the phase angle of the loop remains greater than negative 180 degree at all frequencies below Fc. Step 2, we calculate the needed phase boost. The desired phase margin is specified at phi of phase margin is 60 degrees. The required phase boost, phi boost at crossover frequency, is calculated as follows. Again, the phase for the system is going to be the power stage plus the controller phase. So it's going to be negative 180 degree plus phi of the phase margin. and it's going to be negative 90 plus the phase of boost. Therefore, the phase of boost gives us 108 degrees. Noting that the GPWM and KFP produce zero phase. Therefore, we don't even put it in this equation, the pulse width modulation and the feedback. Because they don't have any capacitors and inductors, and the capacitors are in the inductors are the one that actually cause the phase shift. And then we calculate the control gain at the crossover frequency. So GOS at the crossover frequency is going to be GC times GPWM times GPS times KFB, which will be equal to 1. FC is 1 kilohertz, and GPS at 1 kilohertz is going to be 24.66 dB. In other words, it's 17.1. And therefore, we have GPWM, which is 0.556. GPS, or power stage, is 17.1. And KFB, the feedback gain, again, we have it from here, I think. Yes, it's going to be 0.2. That's going to be equal to 1. Therefore, the controller gain in the crossover frequency is 0.5263. And we calculate the other parameters. Omega is going to be omega square root of omega z omega over omega p. Therefore, K boost is going to be omega p over omega z. Going to be tangent of 45 degrees plus phi boost over 4, which gives us 3.078. And therefore, FC is FC over K boost, gives us 324.9 hertz, and FP is going to be K boost times FC, which is going to be 3000 hertz or 3 kilohertz. And finally, KC is going to be JC FC omega z over K boost, which gives us 349.1 hertz. Now, for the implementation of the controller by an op-amp, again, we have the equation for JCS, which is going to be KC over S, and it gives us 1 plus S over omega 0 square over 1 plus S over omega of the pole square. Now, this is a demonstration of a controller using an op-amp. We can find R1, R2, R3, and C1, C2, C3 using the following equations. C2 for this particular case is going to be omega z over Kc omega p R1, which gives us 3 nanofarads. C1 is going to be C2 omega p over omega z minus 1, gives us 25.6 nanofarads. R2 gives us 1 over omega z C1, which is 19.1 kilo ohms. R3 is R1 over omega p over omega z minus 1, gives us 11.8 kilo ohms. And C3 is 1 over omega p R3, which is 4.4 nanofarads. And this is the PSpice simulation for that exact example that we have. Again, we have the op-amp controller system. We have a feedback going into this, and then we have it going through the switch, and we give it as a pulse to control the duty ratio of the op-amp to the switch. And yeah. And here on the bottom one, you can see the output voltage at different times as well. Now, the other type of control system that we have is called the current program control. The peak switch current is another input to the converter controller besides output voltage in this system. It's a little bit more complicated than the voltage control system. Here, again, we have a clock system, a latch, which is technically a small memory, we have the analog comparator, and we have the feedback going through a voltage controller. And in the voltage controller, we have the reference voltage, we have the output voltage example going through a compensator, going back to the comparator, and then generating a signal using the latch and the clock, and finally feeding it back to the switch. So the middle part, which is an analog comparator using an op amp, the clock, and the latch, creates the current program controller. And by the way, there are different ways to design a current program controller. This is just one method. So the current program control versus the duty cycle control. The advantages of current programmed control is it has a simpler dynamic. Inductor pole is moved to higher frequency. It has a simple, robust output voltage control with large phase margin and can be obtained without use of compensator lead networks. It is always necessary to sense the transistor current to protect against the overcurrent failures. We may as well use the information during normal operation to obtain better control. The transistor failure due to excessive current can be prevented simply by limiting IC. The transformer saturation problem in bridge or push-pull converters, and I'll explain about bridge and push-pull converters, can be mitigated. And the disadvantage is that it is susceptible to noise. And it's a little more complicated than the voltage controlled. And we have an oscillation for these above 0.5 or 50%. The current programmed controller is inherently unstable for these above 0.5, regardless of the converter topology. So keep this in mind. The controller can be stabilized by adding an artificial ramp. The objectives for this section would be stability analysis, which I don't think we have enough time to finish. Let's see if we can finish it. And to describe artificial ramps schematics. So for inductor current waveform, the CCM, we have the following ripple current, and the inductor current slopes M1 and negative M2. For a buck converter, M1 is 1 over L, and negative M2 is negative V over L. There's a small typo there. And for a boost converter, it's going to be VG over L, and M2 is going to be VG minus V over L. And for a buck boost converter, it's going to be VG over L and V over L. For a steady state inductor current, the waveform would look like this. Again, we have the ripples. IL DTS is going to be equal to IC, which is IL0 plus M1 DTS. And when we solve for D, we get D is equal to IC minus IL0 over M1 DTS, M1 TS. And for the second interval, ILTS would be IL0 plus M1 DTS minus M2 DTS. And in steady state, 0 is equal to M1 DTS minus M2 D prime TS. And finally, M2 over M1 is D over D prime. And you can see the current and the steady state waveform and perturbed waveform as well. And you can see the small shift between these two, which creates a small current difference between them. And changes in inductor current perturbation over one switching period is shown here. Again, all of these are just for your knowledge. None of them would be actually the exam. And changes in inductor current perturbation over many switching periods gives us this. IL hat NTS is going to be 0 and infinite when negative d over d prime is less than 1 and negative d over d prime is greater than 1. So for stability, d must remain less than 0.5. Now, this shows an example of d equal to 0.6. And in this example, you can see that we're going to have a destabilized system. So in here, alpha is negative d over d prime, which is going to be negative 1.1. So we're going to have a distorted signal, as you can see. And this is an example where a stable operation for d equal to less than half or 1/3. And here you can see alpha is negative 0.5, and you have a merging and very stable situation. For stabilization via addition of an artificial ramp to measure switch current waveform, we can add an artificial ramp. The transistor will switch off when IA-DTS plus IL-DTS is equal to IC, or in other words, IL-DTS is equal to IC minus IA-DTS. And we have the same current program controller. The only difference is we have an artificial ramp added here, and this artificial ramp compensates and makes the system stabilized. And when we have this, we can have d's greater than 0.5. So a steady state waveform with artificial ramp, IL dt is going to be IC minus IA DTS. And this is IC minus IA. And by adding this artificial ramp, so before this artificial ramp, the signal would go to IC, and you're going to have something like this, okay? And when you have the artificial ramp, instead of hitting the current hitting the max here, it's going to hit the max here. And if you continue this, you can see that we can compensate using the artificial ramp situation. And we can see it for the stability analysis using the artificial ramp. Again, here we have the artificial ramp for the transistor. And by using that, we would compensate and make the system closer to the steady state for. So only point that you need to get from this, if d is less than 0.5, then everything is okay. If d is greater than 0.5, then you need to have the artificial ramp, okay, to make the system stable and work in a steady state. Is it clear? So the only thing that I just wanted to show this with the graphs to you. So stabilization analysis, we have this, again, you can read faster than I can. We have the change in perturbation over complete switching periods. We have the first subinterval, the second subinterval, and the net change over one switching period. And after n switching period, and finally the characteristic values, which is going to be the alpha and IL and S in the system. Again, you don't need to memorize any of these equations. This is just proof. So the characteristic value of alpha is equal to negative 1 minus MA over M2 over D prime over D plus MA over M2. For stability, requires the magnitude of alpha be less than 1. And for a buck and buck boost converters, M2 is equal to negative V over L. So these are going to be, again, theoretical problems that you may see in your exam. So if V is well regulated, then M2 is also well regulated. A common choice MA is equal to 0.5 M2. This leads to alpha being -1 at D equal to 1 and alpha less than 1 for D between 1 and 0. The minimum alpha that leads to stability for all D. Another common choice MA is equal to M2, and this leads to alpha being 0 for D between 0 and 1. And the peak current mode control again looks like this. We have the clock given to the flip-flop. Again, this is a peak current, not the current mode control system. And we have that controls the switching. By the way, SW, the switching. And again, a feedback goes to a controller, the comparator, and we have the clock and the flip-flop. And also, we have the slope compensation for D's greater than 0.5. Now, again, in this system, we have the slope compensation, which limits the maximum to keep the system in steady state. And the control graph looks like this. We have the controller, the peak current mode controller, and the power stage, and given back to the feedback to this of the system. Because we are running out of time, I'm gonna just go quickly through the simulation. We have another example here. The first example that we had, here the phase margin is again 60 degrees, and the feedback KFB is going to be equal to 1. Now, here we can see the gain, the output gain, and the output phase. And again, we have a switch in the phase around 50 hertz. And the phase reaches its steady state at -90 degrees at around 5 kilohertz. And the gain reaches -29.33 dB. Which you can see here as well, the PSpice modeling. And the controller for the system, GCS, is going to be K over S, 1 plus S over omega of 0 over 1 plus S omega P. FC is going to be square root of FC FP, which is going to be F square root of FP over FC gives us tangent of 45 degrees plus phi boost over 2. And GCS times GPS is going to be equal to 1. Now, to solve it using the same op amp, R is going to be equal to 10 kilo ohms, C2 is going to be 30 picofarads, C1 is going to be C2 omega P over omega Z minus 1, which is 380 picofarads, and R2 is going to be 350 kilo ohms. And here you can see the total system in the PSpice simulation. And this actually gives us the flip-flop and latch. Flip-flop is actually a latch with a clock. And if you have had digital design with me, you already know this. If you haven't this semester digital design, you're going to learn about the flip-flops and also latches, which are two NOR gates or NAND gates with a feedback, and one of them is giving a feedback to the other one. And we have the competitor, which is an op amp. You already learned about this. And we also have the compensator as well, which is another op amp, an LM324 and an LM111, which all of these, again, are connected to the switch, the output, to be able to control the switch in the system. So this gives you the total, an example of a peak current control mode system and a DC to DC converter. Now, the summary for what we learned today: the design of a feedback controller in power electronics, the need for feedback controllers in power electronics, basic principles, specific focus on regulated switch mode power supplies, regulated DC power supply. We learned about the voltage mode control and the peak current control, Okay, thank you so much. That's it for today. I will post another quiz this weekend for the online students, and I will see you next week. Thank you.